All right, thanks for that introduction. So the name was pronounced pretty good. Thanks a lot. So I work for SUSE as a day job. I do the sleep maintenance, but that's not what I'm talking about. I'm actually talking about my Hack Week projects that I do together with a couple of colleagues and with community guys. And this is basically porting openSUSE to ARM. So why ARM? So openSUSE already runs on pretty much everything. So your laptop, your desktop, your server, right? So my question is there anything more than just those normal devices that everyone has? So the question that I would like to start with is, what about openSUSE on this very little, tiny, neat device? It's very small. If you look closely, it has all the interfaces that you normally look for. So it has an HDMI output, it has USB, it has Ethernet, but it's a different architecture. Or about this one, this is a QB board. It's also the same range of hardware. It has similar input and output. Or this board, it's actually a Beagle board. Or what about, if you go really far away, what about a Raspberry Pi? So there are also fruits in this architecture. One thing I learned about Raspberry Pi a couple of weeks ago was that there was a college professor in the US that assembled together with his kid a big super cluster of ARM computers just to learn and to educate people about working in clusters. So I just added a picture because I thought it's kind of neat. So he bought 64 Raspberry Pi nodes and assembled them with Lego and connected lots of Wi-Fi and so on with wires and so on. So it's kind of neat for a playground. But getting back to more serious things, so currently there's also some movement in the market for ARM processors in server architectures. So here you can see two examples that are in the market or almost in the market from HP and Dell. So they're pretty similar. So you have very high packed rate of servers blades basically in one rack mountable box. So how did we start with openSUSE and ARM? So first of all, I would like to say some words about ARM. So what is ARM for those people who don't know yet? ARM is, as far as I know, the most popular CPU architecture. There are more than 25 billion devices that have ARM inside. Of course, most of them are your mobile phones and little small routers and appliances that you don't actually know that it has a computer inside. But still, it's a quite impressive number, I think. Their slogan is low power leadership. So this gives a pretty good impression on where we are heading. They offer designs that are optimized for system on a chip. So this means all I/O ports, everything that you need to run a full computer is usually in one chip design. They offer various designs from very low end embedded kind of niche to more desktop-oriented or more server-oriented architectures. So for openSUSE, there are two interesting profiles that we care about. So one is, I would call the classic profile. It's ARM version 5 or version 6, so that's what you get in the Raspberry Pi, for example. It's very low power consumption. It has reasonably low performance. It often doesn't have native hardware floating point support, so you need to do dirty tricks on soft board emulation. There's also a separate series that is more popular these days. I think it's the Cortex-A series, so it's ARM version 7 inside. It usually has hardware floating point support. It has some SAMD support. It supports up to 1 terabyte of memory, and in the newer variants like Cortex-A15, and the new variants even have virtualization capabilities. So pros and cons, just to give you an introduction. Overall, I think it provides a pretty good performance per joule ratio. So that means the raw absolute performance is not that high, but it seems to have an advantage over other architectures when it comes to power consumption, but you have to look at the whole system, so it really depends on which particular server, which particular CPU and so on you compare. But the general trend, at least at the moment, seems to be that it has a power consumption advantage. And due to the low power leadership, it seems to be interesting for workloads that is not primarily CPU bound. So if you're looking for high performance computing that really needs a very performing CPU, then ARM is probably currently not the best architecture, but for everything else it seems to be an interesting option. Okay, so first of all I would like to start with the magic black box as usual. So when we build an openSUSE distribution, we have lots and lots of packages. We have this black box that we call the build service, and then after a while and lots of magic things that happen, there's a DVD. So what is the build service? The build service offers a systematic approach for rebuilding a distribution. It tracks all the dependencies between the packages. It has integrated image and installation media building, so it is just one solution. And one thing that we really focus on is to make rebuilds really reproducible. That means if you do only one change in one particular area of the distribution, we can be reasonably sure that the new image that is being created has only this one change included. So we don't have to do retesting everything on every new image build. So just one more thing that I want to go in more detail is how does it look like? So we have internally we have source tarballs, we have a spec file which is kind of a build description that explains on how to actually build a particular package. And for each of those we set up a build environment, which is basically an environment where the package can be built. This is described more in the spec file. You have a base system, and we run this usually on normal x86 hardware with a normal kernel running. If the build succeeds successfully, you get a binary package. But actually, it's not actually that simple what I just told you. So in order to make the build reproducible, we actually do all the builds in a sandbox. So there are many reasons for that. The sandbox provides us basically a way to lock down the build. So everything that happens within the sandbox has no network access, it has no access to the actual physical hardware, and it runs with minimal privileges. So obviously we do that for security reasons, so we want to avoid that a malicious build job would take over the machine or would inject certain things that would harm the build cluster. But it also helps to make the build reproducible. So if the build doesn't have any way to access the network, it cannot fetch stuff from the internet in order to complete the build or something like that. So there are some packages that originally try to bootstrap or configure or download something from the internet, and that would actually harm of being able to build it would actually harm to have a reproducible build, because we can't actually control what is outside, so we try to contain everything in the sandbox. So the setup is a little bit more complex than originally I presented it. And on all the other architectures like x86 and PowerPC that we support so far, we use virtualization. So either we use KVM or Xen in order to produce the sandbox. On ARM, however, by the time we started the port, there was no Xen support available. So I think meanwhile, there have been some announcements about pre-production or experimental port of Xen for ARM. We have personally not tried it yet. But at the time we started, the thing was not available. Also, the hardware that we actually had available for testing didn't have any hardware capabilities for virtualization. So we were kind of stuck on how to do a sandbox build. So the idea that we started with is, okay, we use QEMU, which is an emulator that provides reasonably good performance for emulation. It can do hardware emulation, so it can do a full system emulation, but it can also just do a system emulation. So this is the setup that we actually started with. So you can see it's pretty much the same like before, except for this tiny CPU emulation layer between the Linux kernel that is running in the sandbox and the build system for the ARM environment. So the advantage we have here is that the sandbox is running virtualized, so we don't actually lose any performance. It's near native hardware speed, and if we run on a pretty powerful x86 box, this gives us pretty decent performance, at least we think so. We can also reuse the host kernel, so we don't need to get into all the getting your first kernel on ARM to boot stuff. We can start with the kernel that we already have. And only the ARM build environment is actually run in the emulator, so this is also helping a bit with the performance. But on the other side, everything that is actually run in the environment is run in the emulator. So one thing that we often get asked is, why don't you do cross-compiling? And the main reason is cross-compiling works pretty well for a small set of packages, but in order to build a whole distribution, you would have to patch a lot of packages, and you have to maintain these patch sets because not everything can be upstreamed properly on your own. That's quite a lot of work. There are a lot of people who have tried to do that, and I think a lot of them failed, and because it's a quite tedious and not very successful job overall. There's also a principal disadvantage with cross-compilation. You can't actually run the binaries that you just built. So in cases where you need to run some code generator that was built in between, you can't actually run it, and you would need to do lots of dirty tricks in order to actually build successfully the package. So on the other side, if we do emulation, we have to emulate everything that happens. So for really good emulation, so that the package doesn't actually notice that it's running on a different architecture, we need to emulate all the syscalls. There are also lots of I/O controls that we learned about. One funny thing is that we noticed we also need to emulate certain files in /proc. So for example, I think it was /proc CPU info or something like that, where certain packages noticed, okay, I'm supposed to build for ARM, but proc CPU info says it's x86-64. That's not something I can work with, so we had to patch QEMU to actually extend the emulation to also fake certain files in the environment. And there are also some special protocols between the kernel and the user space, like netlink. So that one is currently not implemented, but as we try to build without network, it's not really relevant for building. So there's no network, and so we don't actually need to emulate it. And one thing that we learned is to actually find possible emulation bugs or to find discrepancies where we need to actually fix the build environment is to run test suite. So that really helped us in finding the last problems that we had. And currently, I think we're in a state where we believe that there's no bug in the build just due to emulation. So everything that we need is actually working. So this is one graph that I collected. It's kind of faked up. It's just to give you a rough impression on how fast building would actually be. So the red bar is the one with QEMU, with the system, with the user emulation that I was just describing. The Cortex A9 bar is basically the native hardware that we had available. So we did also internally for cross-checking a build in on native hardware. And the lower one is x86, so the regular architecture where we build on. And as you can see, if we would sum up the rebuild times for all the packages, which means, okay, you would build all the packages one after the other on one single machine, it would take almost half a year. So that's not really a workable solution. So we thought again, maybe full CPU emulation is not the right approach. And the trick that we came up is actually quite neat. So in the build environment, there are many binaries run during the build that are not actually architecture specific. So for example, the first thing that usually happens is you copy a tarball somewhere and you unpack the tarball. The tarball is usually compressed, So what you do in the normal emulated environment is you run the uncompressing command in the CPU emulation. But that's not actually necessary because the x86 binary does exactly the same thing. It will uncompress it exactly the same way like the ARM binary would do. So what we can do in the build environment is that we can fake up a kind of a cross-build system, that's the way I call it, that contains certain replacement binaries that are running in the native architecture of the build host, and that way we can easily speed up the build. We can also replace a few more components, like for example the compiler or the linker. I think we stopped replacing the linker, I'm not sure. We're still using the linker replacement. So that gave us a tremendous speed up because we are kind of building cross, but the build system doesn't notice it because for the build system it looks like a native compiler, which is kind of neat. So just to give you a comparison, now the red bar in the graph is the accelerated build. So that's the one with our speed up hacks. And as you can see, we have almost doubled the performance of the rebuild. It's not quite on the level of native build, so there's still some way to go. But it's a workable speed up. So the question is, does it actually build? Okay, yeah, it does build. Next question, does it actually run? So what do you think? Raise your hands if you think it runs. Okay, so most of the people think it runs. That's nice, but it doesn't actually run. And the question is why? Actually, we have two missing pieces that we need to take care of. So the first of all is we actually need a kernel. And so far we were able to build the whole distribution, but we didn't actually build a kernel because we never needed it. And everything built properly except for the kernel. So we had to build, well, really dig into this ARM booting and kernel mess. And the second part is we also needed a deployment method. So first thing I would like to mention is basically the kernel. So with Linux 3.5, I think we have roughly 50 flavors in the kernel tree. So you're very far away from having one kernel image for ARM. So you basically need, for each particular system, a SOC generation, you need a specific kernel. And they're all incompatible to each other. Also, there's one particular oddity is that you don't have anything like a BIOS or EFI or whatever that pre-initializes the hardware just enough so that you can actually load the kernel. So you need to use U-boot, which is a special bootloader that does some pre-hardware initialization, like setting the right voltage for the USB controller and setting up DRAM refreshments and whatever else it needs to actually get far enough to boot the kernel and initialize all the hardware that you need. Of course, you can't build one. You need to really build one for each architecture or for each SOC generation, so you really end up with lots of variations. And every small variation actually requires that you build a particular image for this device. So the obvious solution for us is with the build service, okay, we embrace it. So we have all the capabilities to build many flavors. We have the capabilities to build many images with the same packages inside. Okay, so we thought we will just do it. Of course, everyone else still considers this to be a problem, so there's a lot of work going on to actually sanitize this environment a bit. I think the keyword was single C image kernel support, which means that they try to unify all the architecture-specific ways so that you can end up with less kernel flavors than you have today. So one thing I learned on reading an article, so I'm not very much into the kernel details, is that the ARM architecture tree has a lot of code duplication. It has 27 different implementations of timing or some timer support, and all of them are kind of incompatible. And they're trying, well, currently they're trying to unify this, so there's ongoing work to build up a new infrastructure with common API and common architecture-specific abstractions. And the plan, as I learned it from this article, is that we will roughly end up with 4 kernels for ARM. That's a pretty working solution, I think. Okay, so we kind of sorted out the kernel stuff. The second part is we actually need a deployment method. So for deployment, we use Kiwi. And the usual challenge is, okay, we usually build CD images, but we have this device, and it doesn't actually have a CD drive. It's not even big enough for a CD drive. So we need a different way. Also, doing an installation media is not actually working due to the fact that I just explained before. You need a specific U-boot and a specific kernel for each device. So you can't actually build one CD that would boot on all the devices. You need really one specific image for one device. So what we added instead in Kiwi is basically, as a first step, a generic change root target. So that one is just building you a change root tarball that you can unpack on a machine that has already a working kernel from somewhere. If you got it a different distribution, if it has some Linux pre-installed, like Android or something like that, you can unpack the image and you can change root into it if you have root capabilities, of course. And then you have already a start for openSUSE distribution. Of course, you need to actually then dig into the more hardware-specific details. And for all the other hardware that we have available, we started to build images or appliances that have basically a minimal distribution already installed to combine with the right bootloader, with the right kernel. And you can just DD it to your SD card and boot from it, and it should work. So the question, okay, does it run? Just want to give you the answer, yes, it does run. If you want to see all the details, there's a workshop today in the afternoon at 3 o'clock, I think, in some room upstairs. And if we have a long collection of devices there, you can bring your own device and we will try to enable it, or we will try to help you enabling it. And yeah, so just to show you the hardware that we currently have, we have FKMXs there, BeagleBoard, PandaBoard, IMX from Freescale, and we are also working on some other devices. So there's some effort from Bernhard Wiedemann, for example, to work on a Raspberry Pi image. Of course, you are invited to contribute, so you can test our images. If you have the same hardware, you can try to provide us other test hardware, and we will try to take a look at it. Or if you have hardware available, you can help us with filling the missing pieces. That's actually quite easy. So we have build service projects, so everything is under build.opensuse.org. Currently, we have 12.2 openSUSE enabled for ARM. We think the port is pretty stable. And we have lots of sub-projects there. So there are already community members, or sometimes our own, providing particular device enablement for particular devices. And the interesting part is the circled red ones. You can create your own sub-project there. Okay, I'm already running a bit out of time, and this was actually a talk for 1 hour, so